with speaker. I was using this computer last night at home and messing around with the sound settings. So this is set on digital output. There's the problem. So confusing. Alright, now let me try it. Oh, but now the master volume is muted. Now let me try it. Ta-da! Alright. Oh good, other people are here. I was thinking I was in the wrong place this morning. Usually Jace and RJ are there right away. Alright, so here's what's going on. Let me just take you through the rest of the semester. Today, a little bit about the greenhouse effect and global warming, just a bit. So I've got some questions here that I thought would be good questions for you to know the answer for you to have answers to. How does the greenhouse effect work? That's what I'm going to go over briefly today. What are the predictions of climate models? You probably heard some of this, but I want to go over it again. And how do we know that they're valid? So there are all these climate models. People say that the temperature of the Earth is going to increase by this amount in this amount of time, or it'll be between this number of degrees and this number of degrees, assuming that we don't change what we're doing. How do they know that's true? Because a lot of people think it's not true. And that's what I want to address. Who do you believe? You believe people who say, oh, well, here's the other question. How do we know that humans are causing global warming? A lot of people say global warming is, sure, it's happening, but we're not responsible. There's nothing we can do about it. It's not anything we're doing. It's just a natural cycle. So, and then the next part, what can we do about it, if we can do anything at all about it? So today, I just want to kind of briefly go over how it works, because we've got some other stuff to do. In here, the people who are here have a couple of quizzes. And today we need to get the climate map projects in. I've got this note in yellow. They're due today, but if you don't get it in today, still turn it in. If it's not done today, I guess I should change that to say, if it's not done today, don't turn it in yet, but still turn it in. So they're due today, but if it is not finished, don't turn it in yet. Do turn it in before, before the end of the semester, or it'll be a 0, and that'll be really bad. But I don't think anybody's going to get a 0, because as far as I've seen, just about everybody has started it. If you haven't started it and done anything, then you could get a 0. That would really hurt your grade. So that was me editing my web page. I'll have to refresh in a little while. So there are 3 things to do today. One is to talk a little bit about how the greenhouse effect works. Second, I'll help some of you, check in with you about turning in your climate map project, what you have to do, that kind of stuff. And then third, science courses for next year. So it's a little bit messy this year. You're lucky because you took a science class during the first semester. There's some people who won't take their science class until second semester, and science teachers are the ones who recommend you for your science class for next year. So you've got me. I can tell you about the classes. I can make a recommendation. So that's all good. All right, greenhouse effect. Got a couple of links. What is the greenhouse effect? There's a little link there. And then there's how does it work? And I was reading up on this. I feel like I understand it pretty well based on the chemistry and the physics, but I ran across some information that's kind of new to me that I'll share with you, but I'm still not really sure how to digest that. First, I'm going to click this link, and we're going to get to a FET simulation that looks kind of like this. This is the sun, and you can see waves coming from the sun, and then you can see the sunlight hitting the earth, and then you can see these other waves leaving the earth. But they don't all exactly leave the earth. Some of them come up and they hit these molecules in the atmosphere. And they're showing 3 different kinds of molecules. There's CO2 there's H2O, and there's CH4. So H2O, everybody knows that's water. It's actually a greenhouse gas. And CO2, that's the one we talk about the most in terms of the greenhouse effect of global warming. And I'm breathing that out right now. We're all breathing it out. You drink a carbonated drink, you're drinking it. And then this other one, CH4, is methane, and that's the number 3 greenhouse gas. The biggest greenhouse gas is really water, but that's something that has been here and is going to continue to be here, and it gets complicated. But CO2 is the most unnatural, I guess, between water and CO2. This is the one where we're burning fossil fuels, we're producing that. Like I said, it's really complicated. Water plays a role too, but really this is the one people focus on, and also methane. Before I go to the simulation, I think you can understand a bit of this. Look at the wavelength of this. Look at the wavelength of that. So what they're showing here is that visible light, mostly visible light, comes in from the sun and hits the earth, heats up the earth, and then the earth and everything around it gives off infrared. And that's what this is. This is longer wavelength infrared. Visible light comes right through the atmosphere, mostly. You can see some of it hitting this cloud and not making it through, but others gets through here. But the infrared, when it's on its way out, it gets blocked, at least partially, by the greenhouse gases in the atmosphere. So the visible light comes in, heats up the earth, the hot earth gives off, it radiates heat in the form of infrared radiation. That hits the CO2, energizes it, and then the CO2 actually gives off its own radiation. Some of it goes out into space and some of it goes back. So it's the stuff that goes back. That's what's heating up the earth. If all that happened is the sun heated up the earth and then this radiation went back into space, it'd be a much cooler place. In fact, humans wouldn't be able to survive. So now, with no further ado, let me go to the FET simulation. I'm going to open up the Java version because I can go full screen. But if you want to try this on a Chromebook or something, just click there and it'll do the browser compatible version, even if you don't have Java. I think I'm opening it. Do I already have it open here? It's just being a little slow. Everything's slower when I'm streaming. And I forgot to make my window with my picture there, if anybody's missing me watching the stream later on. Alright, so this is the greenhouse effect simulation. And we've got yellow up here. And if you look in the top right of my screen, it says that's a sunlight photon. Turning off the light so the people in the classroom can see better. And then the red, they're calling these infrared photons. And I think we're set on the atmosphere today. So that picture, let me jump back to the picture I just showed you. Light has a dual nature. It's a wave and it's a particle. So this picture is showing light as a wave, and this is showing light as a particle. So these are like bullets of light compared to waves of light. But still, the yellow ones, those are visible light, those are shorter wavelength, and the red ones, those are infrared, those are longer wavelength. And the yellow ones, you can see, just keep coming in from the sky. They're just raining down from the sun, hitting the earth, heating up the earth. And when the earth gets hot, the earth gives off these red ones. Now the red ones don't just go back out into space. Some of them do. I mean, that one made it out, that one made it out, that one made it out. But others go up and they kind of bounce all around and then they come back to Earth. And that's because we have, if you look over on the right, we have water, we've got carbon dioxide, we've got methane, and we have, what is that? Is that nitrous oxide? Or, I think it's nitrous oxide. Let me look up what N2O is. N2O, into a chemical name. We don't need the BMW N20. Nitrous oxide. So I was right about that. Now, if I get rid of, I'm going to switch from greenhouse concentration from what it is today down to none. So something just happened there. Like, what's different in this? Do you all see it? Hopefully you see it. The red, the infrared, that's just going right out into space. And I should have had you pay attention to this thermometer over here, which now is at 0 or 1 degree Fahrenheit. Kelvin, we haven't really talked about what Kelvin is. That's just a different way to measure temperature. Now we're at -4, -3. So sunlight's still heating up the Earth a little bit, but that heat that's being released on the Earth is just going right back out into space. So let me switch back to, actually, I'm going to switch to Ice Age. So here we have Ice Age conditions, and if you look in the table over at the top, or on the right, people aren't really sure how much water was in the atmosphere in the Ice Age. That's why the question mark is there. But there was carbon dioxide in the atmosphere, and there was methane, and there was nitrous oxide. And if you look at the thermometer now, it's 28 degrees Fahrenheit. I think that's the average temperature of the Earth, or supposed to represent average temperature of the Earth during the Ice Age. And a lot of the red is going out into space. If I follow it, if you look right up at the top, you can see some of the infrared's leaving. But there's enough of this greenhouse gas in here that some of these are bouncing around. They're hitting the greenhouse gases, they're being re-emitted, and they're coming back to the Earth. And so that's what's heating it up. Looks like we're up to 35, 36, but that's an average global temperature. Even though that's above freezing, that doesn't mean that the Earth was above freezing everywhere during the Ice Age. That was just on average. I'm going to skip 1750. I'm going to go back to today. Actually, let's go to 1750. So, if you look at this little slider, where that is, as I switch from 1750 or Ice Age to 1750, this is going to go up a little bit. Goes up to the purple mark, and these change a little bit. Scientists know what these are. They know how much carbon dioxide was in the atmosphere back in 1750. Does anybody know how they do that? They can't travel back in time. Tommy, you know?
Don't they get it from like ice?
Yeah, they drill, they get cores of ice, and they can analyze the gases trapped in the ice from 250 years ago, and they can figure out what the atmospheric concentrations were. So the average temperature then, according to this, 61 degrees Fahrenheit, 1750. Now if I go to today, we've got some more modern stuff here, and the greenhouse gas concentration bumped up a little bit. This isn't actually today's concentration. This says CO2 388. That was when this simulation was created. And I don't know, I can't see on the page here any date at which they did this, but the CO2 concentration, I'm fairly certain, is over 400 parts per million now. Let me check on that. I'll let this go. People monitor this really carefully. Today's is maybe a misnomer. Today's CO2 concentration. There's daily. So the average in 2019 was 409.8 parts per million. If you go to this, CO2 Earth. I don't know if they can really monitor daily CO2, but I'm kind of curious. So January 17th, 2021, we're at 414, and January 17th, 2020, 412. Apparently, we've produced the amount of CO2 we've released, or our carbon emissions have decreased this year because of COVID, because people are driving less. But it's still going up, the levels in the atmosphere. All right, so if I switch this to lots, this would be just crazy, tons of CO2 and methane and nitrous oxide in the atmosphere, and that temperature is going to go way up. 68, I don't know. I don't know how high it would go, but this could be bad. We wouldn't want it to be there. Go back to today. There's some other things I could do here, but I don't know if I'm going to really bother with them. This is just showing, it's making the comparison to a greenhouse, an actual greenhouse that has glass panes. And this is the part that I'm not certain this is really the way greenhouses work, but sunlight comes in, goes right through the glass, heats up the plants down here, which would be the green area. And then those warm plants give off infrared, which you can see some of the infrared gets through the glass, but some of it, with every pane that it passes through, a lot of it bounces back. I was reading this morning that in an actual greenhouse, the main thing is that the air is just trapped down here and the air gets hotter, and you can't have any convection getting out of the glass. So that's the main thing that causes greenhouses.
Would it really be 190 degrees?
100, yeah, in a greenhouse, greenhouses can get really hot. But this is triple pane. Let me reset and go down to one pane of glass. But actually, so Tommy was just saying, would it really get to, what was that, 190 degrees? It probably depends on where your greenhouse is. If it's in a really bright place on the equator with lots of sunshine, maybe it could get that high. Let me do just one panel of glass. It's 89, 90. The other thing about when you have multiple glass panels, there's less heat loss from, well, air leaking out, and also from conduction. We haven't really talked about that, so I don't want to get into conduction. It looks like one glass panel, we're getting up to 82, 80 degrees. I don't know. I've never heard of a greenhouse that was almost 200 degrees. But I have made a solar oven that got up to 450 or 500 degrees. And the solar oven just had sunlight coming in, and it had a glass panel, but it also had reflectors to kind of funnel more sunlight. So that's how the greenhouse effect works. I'm just going to put this on today and summarize it. Sunlight comes in, hits the earth heats up, gives off infrared, and the infrared radiation doesn't make it through the greenhouse gases. There's this last thing that I haven't really shown you. This is showing what happens when a photon hits a methane molecule. So notice how some of the photons of infrared, these are the ones, this is like heat leaving the earth. Some of it can pass through, but every once in a while it hits the CH4, and the methane takes in the energy. Sometimes it kicks it back out into space, but sometimes it kicks it back to Earth. And that's what heats things up. So it's not like greenhouse gases are a perfect wall that keep the heat in. But they're just good enough at keeping some of the heat in some of the time that it increases overall. If I switch this to visible photon, always goes through. So sunlight can always get in through this, but infrared can only get out most of the time. If I switch this to CO2, There's carbon, and it's got 2 oxygens. I don't know if how sophisticated this simulation is, but CO2 is not as powerful greenhouse gas as CH4, as methane. But there's more of it in the atmosphere. So the effect of CO2 right now is bigger than methane. But same kind of thing. Some of these, a lot of the infrared can actually get out of the atmosphere, but some of it can't. And it's that some that's heating us up. Visible photons. I was going to say it looks like they passed right through, but it looked like one actually hit the CO2 and kicked off an infrared. Maybe it was just because I had only just switched it. I'm going to do one last one. So this is water. It's like sunlight generally can pass through water as a gas. Not when water is a cloud. That's different. Clouds can stop sunlight, as you know. But infrared, I'm guessing every once in a while, there we go. It looks like more is passing through the water than the other stuff. Although I can't be sure. Let's go back to my website. So that's how the greenhouse effect works. Light comes in, infrared doesn't all get out, and it just gets concentrated. We'll talk about some of this other stuff tomorrow. Courses over the next year. So I want you to complete this assignment in Google Classroom today. And it's Science Course Request Form. There's a form right there. Let me make sure. I think I've got it set to get your email address, but put your name in, just in case you don't put your name in. I need to make sure, collect email addresses. Good. So when you fill out this form, enter your name, and then list any science courses that you would like to request next year. And I'm going to go over what some of those science courses might be and tell you what they're like. You don't have to take a science course next year, but it would be a good idea because you need some more sciences to graduate. So if you'd like to look at this course catalog on your own, just go to the high school website, and I think it's under academics. There may be another link down here, but I know under academics, program of studies, this is where all the courses are listed. And you can view this different ways, but I feel like it's most helpful, I think, to click this link. This is for a PDF version. This link right down here, maybe it's the same one, pop out. I'm just going to click there. And for your other disciplines, for language arts, math, business, all that kind of stuff, you're going to be looking in different places, but I'm just going to go over the science. Sorry for the lagginess. I'm having trouble because of the streaming that I'm doing. Alright, I need to go to page 42. And I'm not sure that 42 up at the top is the same as 42 right there. Almost there. Science. We don't really need to read that. So this is what you're all taking right now. Earth and Space Science 100. So this counts as one physical science credit. And in order to graduate, you need 3 science credits. One of those has to be physical science, and one of those has to be what we call natural science, which is really, I would call it life science. So life sciences are things like biology, botany, sciences where you study living things. And physical science are chemistry and physics and earth science. non-living things. And so that's grade 9. So this is what most people coming out of this class take, Biology 100. So this has been Earth Science 100. Biology 100 is kind of comparable. It's a little different though. I would say we haven't done a lot of math in here, but there's been a lot of, let's talk about volume and pressure and these physical changes and what happens when you heat something up and motions and things like that. Life sciences are a little bit different than that. I would say there's more writing when you get to biology as well. So if you feel like this course was kind of a pretty good fit for you, or it was maybe a little hard for you, definitely Biology 100 would be a good choice. If you feel like this has actually been quite easy, maybe a little too easy, then Biology 200 might be an option too. I'm going to read these and then talk about the differences. So Biology 100 introduces you to biology theories, concepts with class activities, experimentation, and some projects. Hopefully COVID won't be such a thing next year and there'll be more projects and labs in this year. Topics include scientific method and experimentation, biochemistry, cell structure, function, genetics, ecology, evolution, human body systems. And in order to take that, you have to have taken this class, which you've taken. And I don't know if it says, it doesn't really clarify whether you have to pass this class or whether you just have to have taken this class. But everybody, all of you are in a position that you can pass this class as long as you don't drop the ball in the last week here. Then Biology 200, it looks pretty much like the same thing, except I think they've thrown in the word comprehensive. Comprehensive study of biology theories. So there's more. There's definitely more work, there's definitely more writing. And it's 1.5 credits compared to 1. What that means in a normal year is you have it every day instead of having it every other day. And one day you have it full block, the next day you have it a split block. This year what it means is you have it 3 out of the 4 terms. Now I wouldn't recommend that for most people coming out of this class. Biology 100 would be a better fit, but again, if you feel like this has been really easy and you want something that's more of a better challenge for you, Biology 200 could be a good idea. Advanced Biology, that's for grades 11 and 12, so you can't even do that now. Chemistry, 100. So this says grades 10 to 12. Students don't ordinarily take chemistry right after biology, or sorry, right after earth science. Let's see, it says you have to take earth and space science and biology as a prerequisite. So maybe they've changed it this year. It sounds like you really do need to take biology before you take chemistry. If you're really super into taking chemistry next year, you might ask your counselors if you could take biology and chemistry at the same time. For chemistry, completion of or concurrent algebra 1. So you need to either be in algebra 1 or have completed it. Chemistry 200, I don't think you should go into that unless you have taken biology at this point. And when I get down to the math, you need to be in concurrent biology and algebra 2. So I kind of doubt anybody's taken algebra 2. But for chemistry 100, you wouldn't need that. AP chemistry, nobody in here is ready for that yet. Someday maybe. Physics is usually something people take grades 11 and 12. You wouldn't have the prerequisites for that yet. So anatomy and physiology, that's grades 11 and 12. Belize field studies. So this is something that you could do. This is half a natural science credit. So remember, you need 3 credits overall, and 1 needs to be a physical science, which you'll have. 1 needs to be a natural science. So if you took this, you wouldn't have all your natural science credit, but you could maybe pick up another half a natural science credit and then you'd have enough. Be better to take biology too, though. So, curriculum involves content specific to studying the rainforest and marine ecosystems and the geography and culture of Belize. It culminates in a 10-day trip to Belize. The trip and scuba certification are optional and available at an additional fee. Students who take the trip will spend half the time in the rainforest reserve and half the time on an island marine reserve. You'll also visit Mayan ruins and the zoo. Students will complete a service project at a small village school. So that's it's a great experience for some people who, well, the kids that I've talked to who have done it in the past. You don't have to scuba dive, you don't have to go on the field trip, but that's optional.
So is that still being offered?
I think it is. Well, you know, this year, that's a good question. Are they going to, I don't know if they're going to go this year, but hopefully next year. Botany, not yet, but botany is the study of plants, basically, and you can do that when you're an 11th grader. Competition robotics, so you don't need another physical science credit, but you need 3 credits overall, and if you like the idea of robotics, this is something you can do. It's grades 9 through 12, and I'm not going to read all of this, but basically you learn how to make robots, and you're part of a team that, well, I'll read part of this. You develop skills in fabrication and design, gain 21st century expertise in areas such as entrepreneurship and collaboration. All skill levels are needed and welcome, including areas like programming, electronics, metalworking, graphic design, web creation, and non-technical areas like public speaking, videography, and more. So here it says, this will make your existing skills better and teach you a few more. So it's a robotics competition. You'll actually be competing against other schools in robotics competitions, but you'll be part of a team, and you don't have to build the whole robot yourself. You can just assist in whatever way you're able and pick up some skills along the way. This next one, that's for grades 11 and 12. AP Environmental Science, that's a good one too, but grades 11 and 12. Forensics, this is something that you could take at this point. And forensics, if you watch crime scene investigation, that's what this is, basically. I guess I should read it. And this counts as half of a natural science credit or half of a physical science credit, so you can use it for either. This course is a hands-on investigative science course, or investigative. Students will learn how to observe, collect, analyze, evaluate evidence found at a crime scene. Some of the many topics covered will include the analysis of fingerprints, DNA, hair, skulls, blood, and tracks. Emphasis is placed on the development of scientific inquiry. And for this, you have to have taken Earth and Space Science, which you've done, and you have to either be in or you have to have completed biology. So if you want to take this next year, you have to sign up for biology also. And it doesn't matter if it's biology 100 or 200. Marine biology is half a natural science credit. You could take that next year, and it's kind of like Belize, except without the land. Belize was, you go, you study the marine ecosystem and then the rainforest, but here it's just marine biology. Scientific study and organization and dynamics of plants and animals of the sea. So you learn some oceanography, as well as study the marine plants and animals, and factors affecting their environments. Among the environments to be studied are coral reefs, salt marshes, tide pools, beaches, and rocky shores. So, again, on this it says prerequisite biology. I'm not sure if that means you have to have taken biology before you're in it, or if you could take this and biology at the same time. Some of these, notice how this says concurrent biology, which means at the same time. Well, if you're interested in that, though, it's something you could talk to your counselor about, try to get in. Organic chemistry, that's for grades 11 and 12. Astronomy, this is, both of these astronomy courses are more in depth than what we've done this year. And you could take both of them, you could take either. They're a physical science credit, and basically one is everything in the solar system, that's the planetary astronomy. So more details about the solar system. Let's see, what does it say? Explores amazing and revolutionary discoveries about the cosmos. They will cover naked eye astronomy, constellations, formation of the solar system, gravity, effects on the planets, nature of light, how telescopes work, planets and other bodies in the solar system. We've scratched the surface of this, but this would be much more detail if you like astronomy stuff. And then stellar astronomy and beyond, that's more about life cycles of stars and how we know what's in stars. Miss Krug, who teaches this, she just bought herself a nice telescope last year. She's really into astronomy, so that would be good. Looks like we've got another robotics course. So there was competition robotics, and then regular robotics. And regular robotics, let me see, I was looking for the word Mindstorms in here. In the past, they've used Lego Mindstorms to build robots and have different kinds of projects where you do that. It says it combines engineering and science in a playful way, designed for all ability levels. Students will experience laboratory-based planning, experimentation, design, fabrication, programming, problem solving. So I'm not sure why they left out Lego Mindstorms. I think that used to be in here, and I think they're still doing it. I think it's these will all be Mindstorm robots. So, does anybody have any questions about any of these courses or science courses in general?
Is there a particular one that you would recommend us to take next year?
Yeah, without really thinking, just the natural, or maybe I shouldn't say natural, but the usual progression is biology 100. So that it's biology 100, and then if you want to, if you're really you like science and you want to take an extra elective on top of that, then maybe one of the electives that I went over, like marine biology or forensics or robotics. And then later on you could take some other stuff, physics or the organic chemistry or things like that. So I would really recommend for everybody taking biology 100 next year, but there are a few of you who I think you'd be fine. You actually should take biology 200. We can have that individual conversation, but if you felt like this class was really a pretty easy A, then I think you should do two, or even I don't want to say an easy B, but if you feel like this was pretty simple for you, I think you should set your bar high and maybe go for 200. But if you had to work hard in here, then 100 is probably just about right. So this is for most people right here coming out of this class, and then on top of that, an elective if you want. Any other questions? So if you think of other questions, just ask. I'm going to go back to here. So in Google Classroom, this is the last thing I'm going to really ask everybody to do today. Do this by tomorrow, at least. Fill out this science course request form. And let me read what it says in here. Somebody's already turned it in. Nice work. As your science teacher, I can recommend you for specific science classes next year. To help me find the science class for you, tell me what class or classes you would like to take. So when you're filling out that form, just tell me what you'd like to take. If you have any questions, you could put it in the form. You could say, I don't know, what do you think? Do you think I could do biology 200, or do you think it would be too much to take biology 100 in this astronomy class? Or you can put those kinds of questions in there. I also want to throw in that the counselors and parents can override anything I say. So if I say, no, you should take Biology 100, it's the only thing I'm signing you up for, you can just say to your counselor, Mr. Stapleton, he thinks this, but I want to do this, and we're not going to listen to it. So I want you to know that it doesn't matter that much, but the counselors do like to see what the students are wanting to do and what the teacher thinks they should do. They like to see those two things match up. So it's good if we can agree. But that's it. Just do that, and then people at home come back tomorrow. Oh, wait. I want to quickly go over and actually plug in my camera for this because I want to talk about the project and talk about what you should do before you finally submit it. Hopefully my camera will work. Looks like it's going to. Whoops. Uh-oh. It switched. Alright. So I'm going to unplug. Switch cameras here. Oh, come on. I'm having a little technical trouble. I think you probably figured that out. Trying to get the video back for the people who are at home. One last thing, I think maybe this will work. Come on. I don't know. You may just have to go without video, but you can see my screen. And I think you can hear me. So we'll just go with this. So this is the thing that you need to, it'd be a good idea to print them out. I'm sorry that I didn't print one of these out and hand one of these out to everybody who's at home now. But this is on my website, and you can see it on, let's see. I'm having trouble getting these. You can go to my website and go down to one of the previous classes. And I think it's also in Google Classroom. This is listed in your assignment. So it's this PDF version or PDF version of the Climate Map project. But make sure that you really look at this. So I'm going to be doing this. I'm going to look at your slideshow. I'm going to see that it has a title. It makes sense. You could just call it Climate Mapping Project Slideshow or Climate Mapping Project. If you don't have a title, I'm going to give you a 0 there. So just put a title in. Numbered items below appear in the order listed. So I think everything is all set up. I've already given you the template with everything in this order. So that should be easy. So you should get this checklist and kind of check things off. The elements appear one at a time. In other words, video number 2 should only show pressure belts. Video number 3 should only show the pressure belts and winds, and so on and so forth. So if you've done that, if things have appeared one at a time in your videos, each video has one more thing than the one before it, you get points for that. Narration is clear and easy to understand. Some of you are super quiet. You know who I'm talking to. You're going to need to speak up in this, or I'm going to give you a 0 there. Then, for your first slide, title, author, introduction. Did you explain what you're going to do in the rest of the slides? If you did, then check. And did you show your completed map in there? If you did, check. If you didn't, or if you forgot to do this introduction, 0, 0. So, so far, there really isn't, and when I say check, I'm going to give you 3 for that. Excellent. These things so far, if you've done them, you're pretty much going to get 3s. This is where I might start to give some people 2s. So, right here, pressure belts. All pressure belts are included and correctly placed. So I'm going to look at your map, and I'm going to see if this is your map here. Did you have all the high and lows that you're supposed to have? And if you did, you get a 3. If you maybe left one out, you get a 2. If you didn't have any H's or L's, you get a 0. But I don't think anybody's going to do that. So you're going to get at least a 2, so you'll be okay. Explain why the pressure belts are there. If I hear you say the high pressure belts are wherever the air sinks and the low pressure belts are wherever the air rises, you get 3 out of 3 for that. Prevailing winds. All the winds blow in the correct direction, meaning high to low. All of them have the correct curve, meaning clockwise in the north, counterclockwise in the south. And then do you explain why they blow? So basically this is they blow from high pressure to low and then they curve because of the Coriolis effect, clockwise or counterclockwise. So this first part, why they blow, is high to low pressure. Here, why they curve, that's because of the Coriolis effect. So this, I'm not going to go through it thing by thing and thinking about them, but I'm familiar enough with this that if I watch your video and I watch your ocean currents and you don't do any explaining about why some are warm and some are cold, then you're not going to get points for this one. Why are some warm and some cold? So what I'll probably do is I'll just leave this blank, but if anything is missing, like you left out why some ocean currents are warm and some are cold, I'm going to go down here and write a 0 there. And then I'm going to go back and figure out how many points you lost and take it away from 100. So make sure you go through this, either digitally or you print it out and check all these things. Does anybody have any questions? Sorry, my camera is not working on the Google Classroom. Not Google Classroom, on the Meet. All right, I'm going to call the Meet to an end, and I'll see you gold people tomorrow at our next Meet, and we've got some stuff to do in here. Goodbye. Lots of camera trouble today. You'd think I'd never